Welcome to Engineering Solutions. Today we are doing calculations under heat energy, heat 1, practical application of heat energy. As you can see on the board, we have a liquid and glass thermometer, which has a lower fixed point of 0 degrees Celsius and an upper fixed point of 100 degrees Celsius. The thermometer is used to measure the temperature of a liquid at various time intervals, as seen in Fig B. So at 0 degrees Celsius, the corresponding time is T1. At T1 degrees Celsius, that from 0 to T1 degrees Celsius, the corresponding time is T1. From 0 to T2, have T2 here. So we are asked to read and record the temperature and also the corresponding time. And after that, we plot a graph with the rise in temperature and the differential in temperature against time T. So differential in temperature will be plotted on the ordinate, that's the y-axis, then time T on the abscissa, the x-axis. Okay. To get the temperature reading, the corresponding temperature reading, first you need to measure the total length of your thermometer by using a meter rule. So you place your meter rule on the lower fixed point, that is 0 degrees Celsius, to the upper fixed point. So from measuring here to there, at around 45. So from here, the lower fixed point to the upper fixed point is 45 degrees Celsius. So with the 45 degrees Celsius, it means that to get your corresponding temperature T1, we need to measure from X0 to X1. S0 to X1. So measure from X0 to X1 will give us 6.5 centimeters. So to get the corresponding temperature T1, then it will be the length here, which is 6.5 centimeters, over the total length, that is the 45 after measuring, multiplied by the upper fixed point, which is 100 degrees Celsius, to get your temperature, corresponding temperature reading T1. Okay. So 6.5 divided by your upper multiplied by 100 will give us 14.4. So the corresponding temperature reading here is 14.4 degrees Celsius. Okay. To get temperature T2, you put your from X0 to X2. That's around 13.5. So to be 13.5 over 45, multiplying the upper fixed point, 100 degrees Celsius, giving us 30. Okay. So you continue from X0 to X3. Put your meter rule on it. After measuring, you get something around 19.5. You get the value 19.5. So 19.5 over 45. Multiply by the upper fixed point, which is 100 degrees Celsius, will give us 43.3. So 43.3. From X0 to X4, put the meter rule on it, you get 25.5. So 25.5 over the total length of the meter, the total length of the thermometric thread, 45 times 100 degrees Celsius, yeah, 56.6. T5 from X0 to X5. is around 34.5. 34.5 over the total length of the thermometric thread, 45 times 100, 76.7. Okay. Then 37 from S0 to X6. When you put your meter rule on it, you get around 37. The value is 37, so 37 divided by 45 times 100 is 82.2. Let's do T4 again. It seems there's an error. 25.5 divided by 45 times 100, 56.67. So 56.7. Okay. That will give you your corresponding temperature reading. To find the change in temperature, that's the differential in temperature, T1 minus T1. T1 minus T1 give us 0 degrees Celsius. T2 minus T1, that's 30 minus 14.4, 15.6. T3 minus T1, 43.3 minus 14.4, 28.9. T4, 56.7 minus 14.4, 42.3. We have 76.7 minus T1, 14.4, 62.3, 82.2 minus 14.4, even the 67.8. That's the corresponding differential temperature. Okay, let's look at the corresponding time reading. From the time diagram, the clock diagram, I have T1 here, and this at 0 seconds. So T1 is 0. T2, so as you can see, T2 is on the 10 seconds mark, so 10. T3, so from 10 to 20, let's look at number of division. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So 10 division, meaning each small line is 1. So 11, 12, 13, 14, 15, 16. So 16 seconds. T4, 20, 21, 22, 23, in between 23 and 24. So 23.5. So T5, 30, 31, 32, 33, 34, 34.0. Then T6, 39.0. Okay. So we are done with the recording of the rise in temperature, the differential temperature, and the time, the corresponding time reading. We are now going to plot the differential temperature, the rise in temperature on the y-axis, that's the ordinate, against the time t on the abscissa. Okay. So for a standard graph sheet, the ordinate, the number of boxes on the ordinate, 12 boxes. And the abscissa, we have 10 boxes. Okay. Before you can plot, you need to look for your scale, the scale for the graph. Okay. This is going to the y-axis, and this to the x-axis. Okay. So let me redraw my table and bring out the plottable values on the table. I have change in T in degrees Celsius, 0 against 15.6, 28.9, 42.3, 62.3, and last one is 67.8. Okay. Again, the corresponding time reading, T in seconds, 0.0 seconds, 10.0 seconds, 16.0 seconds, 23.5, 34.0, and then 39.0. Okay, so these are the values we are going to plot. This on the ordinate y-axis, this on the abscissa x-axis. To get your plottable values, your scale, for a standard graph sheet, normally these are the values we plot: 1, 2, and 5. That's interval that you can move on your graph sheet. 1, interval of 1, 2, or 5. Okay. So to start with, the y-axis, the differential temperature. The highest on the differential temperature values is 67.8. Okay. So 67.8, subtracted from the origin. So you get 67.8. Then divide by number of boxes on the y-axis. A standard graph sheet, the y-axis, the number of boxes is 12. So 67.8 over 12. 67.8 over 12 will give us 5.65. So over 12 is giving us 5.65. Okay. But the plottable values are always in this range: 1, 2, and 5. Meaning between 1 and 2, we have a value like 1.5. We cannot use 1.5 as a plottable value because it doesn't fall within the range 1, 2, or 5. Between 2 and 5, we have 3 and then 4. These are all not plottable values. Okay, so after dividing 67.8, the highest value, subtract from the origin 0, divide by number of boxes on the y-axis 12, we had 5.65, which is not within this range. 5.65 is more than 1, more than 2, more than 5. Hence, these values can be increased by multiplying each of the digits by 10. So this one tends to 10, 20, 50. So 5.65 falls within this range. 5.65 is less than 10. So we choose 10 as the interval, meaning we move 0. Assuming this is the graph sheet, the y-axis will start 0, interval of 10, 20, 30, 40, upwards. Let's take it again. Your plottable values are always in this range: 1, 2, and then 5. So after doing your interval deduction, the highest value minus the origin, then you divide by number of boxes. For the y-axis 12. So assuming after dividing, instead of getting 5.6, assuming we had let's say 4.8. 4.8 is within this range. So 4.8 is more than 1, more than 2, but it's less than 5. So we choose 5 as our interval, moving 5, 10, 15, 20, 25 upwards. Assuming after dividing, we had something like 26. After dividing, 26 is not within this range. So when you get a value which is not within the range, you can increase your portable values by multiplying each of the digits by 10. This one tends to 10, 20, 50. So this value comes to this range. 26 is more than 10, we don't choose it. More than 20, but it's less than 50. So your interval will be 50. You use 50 as a scale for the y-axis. Assuming after dividing, it has something like 0.3. 0.3 is not within this range, so we can also decrease this value by dividing each of them by 10. So this one tends to 0.1, 0.2, 0.5. So now 0.3 falls within this range, but 0.3 is more than 0.1, it's more than 0.2, but it's less than 0.5, so we choose 0.5 as our interval. Or assuming we had 0.04, 0.042 is not within this range. So to get the value for 0.04, you need to decrease all this by dividing this again by 10, 0.01, 0.02, 0.05. You can see this is more than that, more than this, but it's less than this, so you choose 0.05 as your interval. The same way, assuming we had 80 after dividing, you can see that 80 will not be in this range, neither will it also be in this range, 10, 20, 50. Then we need to increase our portable value by multiplying this again by 10. This one 10 to 100, 200, then 500. You can see 80 will be within it because it is more than this 50. So you come here, which is less than 100, choose 100 as your scale. So you move 100, 200, 300. So that will be for the y-axis. But our value here that we are using, the highest in the y-axis on the board is 67.8. Subtract from the origin 0, divided by number of boxes, which is 12. So 12 divided 67.8 divided by 2, have 5.65, which is not within this range. So we increase the range by multiplying each of them by 10 to 10, 20, 50, and we saw that 5.65 is less than 10, so we choose 10. So here, this axis, we are using 10 as the interval. Now let's come to the s-axis, that's the t-axis. For the t-axis, the highest there is 39. So 39.0, subtract from the origin, which is 0. So 39 divided by number of boxes, standard graph sheet, the boxes on the x-axis is 10. So 39 divided by 10 will give us 3.9. Now 3.9 will be within this range, but it's more than 1, more than 2, less than what? 5. So we are going to choose 5 as our interval. So for the s-axis, we are using 5, interval of 5 as our x, for the s-axis, we are using 5 for our interval. Okay. So the scale for y is 10, scale for s is 5. Now, this is when you want to start from the origin. But if you don't want to start the graph from the origin, the same procedure. But here, instead of subtracting your highest value, the 39, 0 from the origin from 39, then the same way, you subtract the highest value minus the lower value. But here you can see that they are all 0, 0. So it means still we need to start from the origin. But some of the question comes with the values of both the s and y very close to each other. For example, assuming I have a table like this of x and y with values, say 51, 52, 54, 55, or say 57, and here 11, 13, 14. Okay, let me choose interval between 30s. So 30, 32, 33, 35. When you're asked to plot a graph like this, as you can see, the lower value on the s-axis is 51, the highest is 57. You can see the interval, the range is between 51 to 57. So we are starting this graph from the origin, meaning from 0 to 50 will be vacant. Hence, you need to cut off from 0 to 50 and make sure that you don't start this type of graph from the origin. The same to the y. Look, from 0 to 30. So 30 to 35 as the interval. So if I want to use this as an example to plot a graph without starting from the origin, then the highest value will be 57 for the x-axis. So 57 minus the lowest value, minus 51. I will get 6. Then you divide the 6 by the number of boxes. The number of boxes on the x-axis, standard graph sheet 10. So I'll get 0.6. So 0.6, you bring it to your interval, your plottable values. 0.6 will be within, when you bring this with 0.1, 0.2, it's more than 0.1, more than 0.2, more than 0.5, so it will be within this range. So we choose 1 as our interval. 1, 1, 1, 1. But here, we are not starting from the origin. As you can see, we cut off from 0 to 50, started from 51. So for your x-axis, you can do something like this. Instead of starting from 0, we cut off all the value from 0 to 50. So you can start here 50 from the origin. Instead of the origin starting from 0, 50, then the next interval of 1, 1, 51, 52, 53, up to your last one, which is the 57. The y2, the y value, highest 35. So it will be 35 minus the lowest in it, 30, which will give us 5. So 5 over a number of boxes on the y-axis. Standard graph sheet 12. So 5 divided by 12, we will get 0.41. So say 0.42. 0.42 will be within this range, 0.1, 0.2, 0.5. So it is more than 0.1, more than 0.2, but it's less than 0.5. So we choose 0.5. So 0.5 as your interval. But here we are not starting from 0 because we cut off from 0 to 29 off. So you can say you can start from the y-axis. If this is the origin, you can say you are starting from say 29. The next value is 0.5, 0.5. So 29.5, 30.5, 31, 31.5 up to 35. So that is how to plot a graph without starting from the origin. When you see that the interval is very, very close, you don't start from the origin. Just take the highest value minus the lowest value, divide by number of boxes on the axis. X, standard graph sheet 10, Y, standard graph sheet 12. Okay. So now let's look at our main question where we're plotting the differential in temperature against time t. The differential in temperature, we're using interval of 10, and the time in seconds, we are using interval of 5. Okay. So we are plotting. So plotting differential in temperature, rising temperature on the y-axis. Okay. So change in T / degree Celsius against change in small t / seconds. Interval of 10, 10, 10 on the y-axis. So starting from the origin 0, 10, 20, 30, 40, 50, interval is too big. So 10, 20, 30, 40, 50, 60, 70. The interval of 5 for the x-axis. 5, 10, 15, 20, 25, 30, 35, 40. Okay. So first, 40 0 against 0 on the origin. So 0 against 0 will be somewhere here. Let me use a red marker. 10 on the x-axis again 15.6. 10 here, 15 will be somewhere here, so 0.6 somewhere here will be okay. Then 16.0 against 28.9. 16.0 against 28.9, so 16 will be somewhere here. There's 28.9, so almost 29. Somewhere is okay. Then 23.5 against 42.3. 23.5 approximately 24 somewhere here. This side is okay. Against 42.3. So 41, 42. So somewhere here is okay. Have 34 against 62.3. So 34 here, 62.3 somewhere here. Okay. Then 67 against 39.0 against 67.8. So 39 somewhere here. 67.8. More 68. Okay. So now we are done plotting. We need to do our line of best fit. So our line of best fit, you need to get your centroid. So find the centroid. You just need to add all the values on the differential temperature axis. Then add all the value on the time axis. So after adding all the value on the differential temperature axis, how many values? 1, 2, 3, 4, 5, 6. Then divide by 6. So let's start. You have 0 plus 15.6 plus 28.9 plus 42.3 plus 62.3 plus 67.8 divided by 6 will give us 36.15. So your centroid, the y value is 36.15 against the x value, the time axis. So 0 plus 10 plus 16 plus 23.5 plus 34 plus 39.0 divided by the number of boxes, which is 6. So divided by 6, 20.41. So we are plotting 20.41 against 36.15. So this is 20.41, maybe up to 20.5. So somewhere here, close here, against 36.15. So 36, it is 35, 36 will be somewhere here. Okay. So we are getting the value somewhere this way. This is your centroid. Let me use star to denote it. Okay. So meaning that your line of best fit should pass through the centroid. The centroid, that's the center. So you put your meter rule on it. we are not going to get a perfect line because this is not a standard graph sheet. Some of the values may deviate from the original point. So passing through the centroid. We got some sort of this. Sorry. I'm passing through my centroid here. Okay, so the deviation is okay, one line here. Take this point here, because we are not using the original graph sheet, that this has deviated from the original position, so that this will pass here on top. So one deviating here against this to give us the line of best fit. So that's how to plot a graph when given the x and y components. You need to get your plottable values first and make sure that your scale, the plottable values, falls within 1, 2, and 5. Thank you very much, and see you another time on Engineering Solutions. Thank you. And make sure that you subscribe to our channel, Engineering Solutions, the only solution with the Z.